A telescope stares into darkness, capturing light that traveled 13 billion years to reach us. What it sees should not exist. Galaxies blaze where only faint whispers should glow. Black holes devour stars before those stars could form. The universe expands in two contradictory ways at once. Every image Webb sends back challenges the physics we built over a century. Scientists call them universe breakers. The discoveries are confirmed, the math is checked, our cosmology is crumbling. If you enjoy this, hit subscribe. We begin now. Webb turned its mirror toward a patch of sky no bigger than a grain of sand held at arm's length. Scientists expected to find faint smudges, the barely visible ghosts of infant galaxies. Instead, the telescope sent back images of objects blazing with impossible brilliance. These galaxies existed just 500 million years after the Big Bang. Think of the universe as 13.8 billion years old. These objects appeared when cosmic time had barely begun, when the universe was only 3% of its current age. According to every model we built, galaxies at this epoch should be dim, small, scattered clouds of gas, still learning how to form stars. The galaxies Webb found were anything but dim. They shone with the light of billions of stellar fires. Their brightness suggested they contained more stars than our own Milky Way, packed into regions far smaller. One galaxy emitted so much light that scientists had to check their instruments 3 times. No error existed. The signal was real. Astronomers measure galaxy brightness in magnitudes. The faintest objects Hubble could detect reached magnitude 30. Webb pushes past magnitude 32, seeing 4 times deeper into cosmic darkness. Yet even at these extreme distances, these early galaxies appeared brighter than theoretical limits allowed. Some blazed at magnitude 25, making them 100 times more luminous than predictions suggested possible. This discovery sparked immediate controversy. If galaxies could grow this massive, this quickly, then our understanding of cosmic evolution contained a fundamental error. Dark matter, the invisible scaffolding that shapes galaxies, should take billions of years to gather enough material. Star formation, even at maximum efficiency, should produce far less light. Something about our models was deeply wrong. The brightest galaxies appeared clustered together, as if cosmic dawn had ignited multiple stellar cities simultaneously. This clustering pattern contradicted simulations that predicted slow, gradual growth. Instead, the early universe seemed to have hosted a burst of galaxy formation more intense than anything in later cosmic history. Scientists calculated the stellar mass required to produce this much light. The numbers returned values 10 billion times our solar mass, packed into galaxies smaller than the Small Magellanic Cloud. This density should not exist. These galaxies should have torn themselves apart under their own gravity. Temperature readings from these objects added another puzzle. The light spectrum showed signatures of old, cool stars mixed with hot young ones. This combination suggested these galaxies were already mature, already hosting multiple generations of stars. How could they age so quickly? How could stellar populations cycle through birth, life, and death in just a few 100 million years? But this was just the first shock. What Webb found next made these impossibly bright galaxies look almost ordinary. Scattered across Webb's deep field images, astronomers noticed something peculiar. Among the thousands of galaxies, hundreds of tiny objects glowed deep crimson. They looked like rubies sprinkled across black velvet. Scientists informally named them little red dots. These objects measured incredibly small. Most spanned less than 1,000 light-years across. For comparison, our Milky Way stretches 100,000 light-years from edge to edge. These dots were 100th that size, yet their brightness rivaled entire galaxy clusters. The red color itself told a story. Light traveling across cosmic distances gets stretched by the expansion of space. shifting toward longer wavelengths. This effect, called redshift, turns ultraviolet and visible light into infrared radiation by the time it reaches us. The deeper the red, the farther away the object existed in space and time. Webb's instruments measured their redshifts precisely. Most little red dots existed between 600 million and 1 billion years after the Big Bang. This placed them in an epoch called the Cosmic Dawn, when the first stars ignited and the universe transformed from darkness into light. What confused scientists was the combination of properties. These dots were compact, red, and blazingly bright. No known class of cosmic object matched this description. Regular galaxies that old should appear blue from young hot stars. Quasars, the luminous cores of active galaxies, usually show different spectral signatures. These dots fit no existing category. Detailed spectroscopy revealed more mysteries. The light from little red dots contained unusual emission lines, patterns that indicated extremely hot gas moving at tremendous speeds. This suggested something violent happened in their cores. Matter was being heated to millions of degrees and accelerated to thousands of miles per second. Some dots showed what astronomers call a Balmer break, a sharp change in brightness at a specific wavelength. This feature typically comes from dense hydrogen gas surrounding a powerful energy source. The steepness of this break in little red dots exceeded anything seen in normal galaxies by factors of 10 or more. 341 of these objects have been confirmed so far. They appear only in the early universe. No equivalent objects exist in our local cosmic neighborhood. Whatever process created them stopped billions of years ago. They represent something that happened once in cosmic history and never repeated. Scientists proposed several theories. Perhaps they were extremely dense star clusters. Maybe they hosted unusually dusty regions that reddened their light. Some suggested they might be a transition phase in galaxy evolution, a brief moment between formation and maturity that we rarely catch. None of these explanations fit all the evidence. Each theory could account for one or two properties but failed to explain the complete picture. The dots remained stubbornly mysterious, refusing to fit into neat astronomical categories. Then someone suggested something radical. What if little red dots were not galaxies at all? What if they represented an entirely new class of cosmic object never seen before? The universe has a clock. Scientists can measure its age using multiple independent methods, all converging on 13.8 billion years. This number is precise, tested, confirmed across dozens of different observations. When Webb looked back to the cosmic dawn, it found galaxies that should not have had time to exist. Building a galaxy requires time. Dark matter must clump together first, creating gravitational wells deep enough to trap gas. That gas must cool and condense. Stars must form from collapsing clouds. Those stars must forge heavier elements in their cores. Generations of stars must live and die to enrich the cosmic environment with the building blocks of planets and life. According to our best simulations, this process takes at least 1 billion years. You cannot rush it. Gravity works at a set pace. Gas cools according to thermodynamic laws. Stars burn at rates determined by nuclear physics. These are fundamental processes that cannot be accelerated. Yet Webb found fully mature galaxies at 600 million years after the Big Bang. These galaxies contained red stars, the cool, aged survivors of stellar evolution. Red stars form when massive hot stars exhaust their fuel and transform into smaller, dimmer objects. This transformation requires hundreds of millions of years, minimum. The spectral signatures showed more than just old stars. These galaxies hosted complex stellar populations spanning different ages, temperatures, and chemical compositions. Some stars were metal-rich, meaning they formed from material already processed through earlier stellar generations. Finding metal-rich stars this early was like discovering ancient ruins in a land that maps showed as uninhabited. The math simply did not work. If the Big Bang happened at time 0, and these galaxies existed at time 600 million years, Then galaxy formation had to compress into an impossibly narrow window. The first stars ignited around 150 million years after the Big Bang. This left only 450 million years for entire galaxies to assemble, form multiple stellar generations, and reach maturity. Scientists call this the age problem. It ranks among the most serious challenges to modern cosmology. Either our understanding of the Big Bang timeline is wrong, or the physics of galaxy formation is fundamentally different than we thought, or something about these observations is being misinterpreted. Some researchers suggested that perhaps we were measuring the galaxy ages incorrectly. Maybe the spectral signatures that indicated old stars could be produced by other processes. Dust, for example, can redden starlight and make young galaxies appear older, but detailed analysis ruled this out. The spectral patterns were too specific, too detailed to be mimicked by dust alone. Another possibility was that the early universe had conditions we do not understand. Perhaps star formation proceeded faster back then. Maybe the initial density of matter allowed for more efficient galaxy assembly. This would require rewriting textbooks on stellar physics and cosmology. The age problem exposed a crack in the foundation. Every prediction about the early universe relied on the same models. If those models could not explain these mature galaxies, what else might they get wrong? And the situation was about to become stranger still. In July 2024, scientists examining little red dots made a discovery that forced them to question the very nature of these objects. They found one example so extreme, so unusual, that it demanded an entirely new explanation. They nicknamed it the cliff. The cliff showed a spectral feature sharper than anything previously observed. The Balmer break, that sudden change in brightness, appeared almost vertical in its intensity curve. No combination of regular stars, regardless of density or composition, could produce this effect. The team realized they were looking at something fundamentally different. What if, scientists proposed, a little red dot was not a galaxy full of separate stars? What if it was essentially one gigantic object? The idea sounds absurd at first. Stars have specific size limits determined by the balance between gravity and internal pressure. Exceed those limits, and the star collapses into a black hole. But what if a black hole itself became the power source? Imagine a supermassive black hole, millions of times heavier than our star, feeding voraciously on surrounding gas. As matter spirals inward, it heats to extreme temperatures, radiating enormous energy. This energy pushes outward against the infalling material, creating a thick envelope of hot, dense gas. This envelope could glow like a stellar atmosphere. The black hole inside would be invisible, hidden behind the luminous shell. From outside, the system would resemble a single vast star, except instead of nuclear fusion powering it, gravitational energy from the black hole would generate the light. Scientists called this hypothetical object a black hole star. The theory elegantly explained multiple mysteries. It accounted for the extreme compactness of little red dots. It explained why they were so bright despite their small size. It resolved the puzzle of the sharp spectral features. Most importantly, it provided a mechanism for rapid black hole growth in the early universe. Standard black hole formation theory has a problem. To reach supermassive sizes, black holes need time to accumulate matter. They start small, perhaps 10 times our solar mass, and grow by consuming gas and stars around them. But this process has efficiency limits. A black hole can only eat so fast before the energy of infalling matter pushes new material away. Black hole stars bypass this limit. They could accumulate mass at rates far exceeding normal restrictions. The thick gas envelope would shield the black hole, allowing it to feed much faster. This might explain how supermassive black holes reached billions of solar masses before the universe was even 1 billion years old. Not all little red dots might be black hole stars. Some could still be ultra-dense galaxies or other exotic objects. But the cliff provided the clearest evidence that at least some of these mysterious dots represented a completely new phenomenon. scientists had accidentally discovered a missing link in cosmic evolution. Joel Leisure, one of the researchers who proposed this theory, put it simply: these objects might be supermassive black holes in their infancy stage. This was not speculation anymore. Webb was watching them be born in real time. Yet, even as this mystery began to clarify, another discovery was making the situation far more complicated. Galaxies obey rules. They grow at predictable rates. They convert gas into stars with known efficiency. They follow relationships between size, mass, and age that have held true across 13 billion years of cosmic history. Webb found galaxies that broke every single rule. Scientists measure galaxy mass by adding up all the stars, gas, dust, and dark matter it contains. The technique is well established, cross-checked using multiple independent methods. For the early massive galaxies Webb discovered, the mass calculations returned impossible numbers. One galaxy, designated CEERS 746, weighed in at 15 billion solar masses. It existed just 700 million years after the Big Bang. To accumulate this much mass so quickly required converting gas into stars at rates approaching 100% efficiency. In the modern universe, galaxies typically convert 10% of their available gas into stars. The rest gets heated by stellar winds, blown away by supernova explosions, or simply never cools enough to collapse. 10% represents the maximum efficiency observed in even the most active star-forming regions. 100% efficiency means every atom of hydrogen and helium gets incorporated into a star. Nothing escapes, nothing gets wasted. This violates thermodynamic principles. When gas collapses under gravity, it heats up. That heat creates pressure that resists further collapse. You cannot squeeze every last bit of gas into stars without some of it pushing back and escaping. The mass crisis went deeper. These galaxies were not just massive, they were overmassive, exceeding theoretical limits by factors of 10 to 100. The standard cosmological model, called lambda cold dark matter, or LCDM, makes precise predictions about how much matter should exist in galaxies at any given epoch. These predictions come from understanding how dark matter clumps and how that dark matter traps regular matter. LCDM has stood the test of time for decades. It accurately describes the cosmic microwave background, the leftover radiation from the Big Bang. It explains the large-scale structure of the universe, the cosmic web of galaxies and voids. It predicts the abundances of light elements formed in the early universe. LCDM is not a guess. It is a model validated by hundreds of independent observations. Yet it could not explain these massive early galaxies. Mike Boylan-Colchin, an astronomer at the University of Texas, analyzed 6 of the most extreme examples. Each one sat in uncharted territory, exceeding LCDM predictions by amounts that could not be attributed to measurement uncertainty or rare statistical fluctuations. If the masses were correct, Boylan-Colchin stated, we would need something very new about galaxy formation or a modification to cosmology. One extreme possibility was that the universe expanded faster after the Big Bang than models predicted. This would require new forces, new particles, physics beyond the standard model. Some scientists suggested that perhaps supermassive black holes were making these galaxies appear more massive than they really were. A feeding black hole generates tremendous radiation that could heat surrounding gas, making the galaxy brighter and thus seem to contain more stars. This explanation worked for some cases, but not all. The mass crisis revealed a fundamental problem. Either our methods for measuring galaxy masses were systematically wrong, or the early universe operated under different physical laws than we observe today. Neither option was comforting. And then Webb found something that made the mass problem look simple. At the center of most galaxies sits a supermassive black hole. This relationship is not coincidental. Galaxies and their central black holes grow together over cosmic time, maintaining a specific ratio. For every 1,000 units of stellar mass in the galaxy, the central black hole contains about 1 unit of mass. This ratio holds across billions of years and billions of galaxies. Webb shattered this relationship. It found black holes that were not just massive, they were obscenely overmassive, weighing far more than their host galaxies could possibly support. In the galaxy Virgil, located just 800 million years after the Big Bang, scientists measured a black hole mass exceeding 100 million times our solar mass. The galaxy itself contained barely enough stars to account for 1 billion solar masses. The black hole represented 10% of the galaxy's entire mass. This ratio should not exist. In modern galaxies, the black hole accounts for 1/10 of 1% of galactic mass. Virgil's black hole was 100 times more dominant than it should be. The galaxy was essentially a thin shell of stars wrapped around a monstrous black hole core. How could such an object form? Black holes grow by consuming matter. They pull in gas, dust, and occasionally entire stars. But this process has limits. As matter falls toward a black hole, it heats up and emits radiation. This radiation pushes back against infalling material, creating a natural brake on growth rate. This limit, called the Eddington limit, prevents black holes from growing too fast. To reach 100 million solar masses in 800 million years, a black hole would need to exceed the Eddington limit throughout its entire existence. It would need to feed at 5 to 10 times the maximum theoretical rate. Some black holes can briefly exceed Eddington during special circumstances, but sustaining super-Eddington accretion for hundreds of millions of years seemed impossible. Scientists found 12 overmassive black holes at cosmic noon, the period 2 to 3 billion years after the Big Bang when star formation peaked. These black holes were 2 orders of magnitude too massive for their host galaxies. The ratio was not slightly off, it was fundamentally broken. One object, nicknamed BIRD for Big Red Dot, hosted a black hole so massive it defied all formation scenarios. The black hole outweighed its galaxy by factors that suggested it formed first, and the galaxy assembled around it later. This reversed the entire sequence of cosmic evolution. The traditional picture says galaxies form first. Dark matter creates a gravitational well, gas falls in, stars ignite. Deep in the center, a black hole seeds itself from collapsing stars. Over time, the black hole grows slowly, fed by material from its host galaxy. The two evolve in lockstep, maintaining their mass ratio. Overmassive black holes suggested this picture was incomplete or entirely wrong. Perhaps black holes formed first from direct collapse of dense gas clouds. Perhaps they grew from intermediate mass seeds left over from the first generation of stars. Perhaps the early universe had physical conditions that allowed black holes to bypass normal growth restrictions. George Rieker, one of the researchers studying these objects, put it bluntly. Webb had shown that our ideas about how supermassive black holes formed were pretty much completely wrong. The black holes got ahead of their galaxies in many cases. This discovery carried profound implications. If black holes formed before galaxies, they might have shaped galaxy formation itself. Their energy output could have influenced how gas cooled and collapsed. They might have seeded the first stellar populations. The history of the universe might be a story written by black holes, not galaxies. But there was another problem. These galaxies were not just hosting overmassive black holes. They were forming stars at rates that should be physically impossible. Star formation is a messy, inefficient process. Gas clouds collapse under gravity, but most of the gas never makes it into a star. Some gets heated and expelled by stellar winds. Some gets blown away by supernova shockwaves. Some simply remains too hot to collapse. In the best observed cases, about 10% of available gas becomes stars. 10% is the ceiling. No star-forming region ever consistently exceeds this efficiency. The physics is well understood. When gas compresses, it heats up. That heat creates pressure that resists further compression. Some energy has to escape as radiation for the collapse to continue. This process is inherently lossy. Webb found galaxies where 100% of available gas seemed to have turned into stars. Not 10%, not 50%, all of it. Every hydrogen atom, every helium nucleus, compressed and ignited into stellar fire. The 6 most massive early galaxies showed this impossible efficiency. To reach their observed stellar masses in the available time, they would need to convert essentially all their gas into stars with perfect efficiency. No waste, no losses, complete transformation. This violated basic thermodynamics. You cannot convert energy from one form to another with perfect efficiency. The second law of thermodynamics forbids it. Even in the coldest molecular clouds, even under the strongest gravitational collapse, some gas must escape. Heat must radiate away. Pressure must push back. Perfect efficiency is theoretically impossible. Yet the observations did not lie. These galaxies existed. They contained the measured number of stars. They formed in the observed time frame. Something about our understanding of star formation was fundamentally incomplete. One possibility was that the early universe had different conditions. Perhaps gas was denser back then, allowing gravity to overcome thermal pressure more easily. Perhaps the first stars formed through processes unlike anything happening today. Perhaps the absence of heavy elements, which had not yet been created by stellar fusion, changed how gas behaved. Another possibility was that we were missing a major source of matter. Maybe more gas existed in the early universe than models predicted. If galaxies had access to additional reservoirs of hydrogen and helium, they could form more stars without requiring perfect efficiency. Scientists calculated how much matter the early universe should contain. Right after the Big Bang, the universe was nearly homogeneous, with matter spread almost uniformly. Tiny density fluctuations, less than 1 part in 100,000, seeded the formation of cosmic structure. These fluctuations were measured precisely in the cosmic microwave background. From these measurements, astronomers could predict exactly how much matter should clump together into galaxies at any point in cosmic history. The massive early galaxies exceeded these predictions. They contained more stars than should have been available to form them. This suggested the matter distribution in the early universe was less uniform than we thought. Perhaps denser regions existed that our models missed. Perhaps dark matter clumped more efficiently than simulations predicted. Perhaps the seeds of galaxies formed earlier than we believed possible. Each explanation required revising fundamental assumptions about cosmic history. Either the Big Bang produced more matter than we realized, or that matter gathered faster than gravity should allow, or star formation operated under different physical laws in the early universe. The star factory paradox exposed our ignorance. We thought we understood how stars formed because we observed nearby star-forming regions in detail. But those observations captured only modern star formation in a mature, metal-enriched universe. The first galaxies played by different rules, and those rules were about to get even stranger when Webb turned its gaze to cosmic noon. Between 2 and 3 billion years after the Big Bang, something extraordinary happened. The universe erupted in a frenzy of star formation, unlike anything before or since. Astronomers call this epoch cosmic noon. During cosmic noon, star formation rates peaked across the cosmos. Galaxies churned out new stars hundreds of times faster than the Milky Way does today. Entire stellar clusters ignited simultaneously. Gas clouds collapsed in cascading waves of stellar birth. The universe blazed with the light of fresh stellar fire. Half of all stars that currently exist were born during cosmic noon. Not 10%, not 30%. Half? This means when you look up at the night sky, Half the stars you see formed during a 1 billion year window 10 billion years ago. The universe has spent the subsequent 10 billion years merely coasting on that initial burst of activity. Webb's mega-survey, the MIRI-EGS galaxy, and AGN study captured this epoch in unprecedented detail. Scientists used the telescope's mid-infrared capabilities to peer through thick cosmic dust that obscured cosmic noon galaxies from previous observations. The Hubble telescope saw these galaxies as dim red smudges. Webb revealed them as vast stellar nurseries burning through their gas reserves at extraordinary rates. The extended Groth strip, a narrow slice of sky near Ursa Major, became ground zero for cosmic noon research. This region contains thousands of galaxies at the right distance to show us the universe as it appeared during peak star formation. Webb stared at this field for hundreds of hours, building up a comprehensive census of cosmic noon activity. What the telescope found shocked researchers. Galaxies were not forming stars steadily. They were bursting, igniting in violent episodes where star formation rates jumped tenfold or more in just a few million years. These starburst events converted massive gas reservoirs into stars in geological instants. One galaxy observed in the survey formed stars at a rate of 1,000 solar masses per year. For comparison, our Milky Way forms about 2 solar masses worth of stars annually. This cosmic noon galaxy was producing stars 500 times faster. At this rate, it would exhaust its entire gas supply in just 10 million years. The bursts were triggered by galaxy collisions and mergers. When two galaxies collide, their gas clouds slam together, compressing and heating. This compression ignites star formation throughout both galaxies. Webb captured multiple galaxies in various stages of merging, watching star formation burst to life in the collision zones. Cosmic dust shrouded much of this activity. Dust absorbs ultraviolet and visible light from young stars and re-radiates it as infrared. Previous telescopes, optimized for visible light, missed most of the action. Webb's infrared vision cut through the dust, revealing the full intensity of cosmic noon star formation. The survey also revealed something unexpected. During cosmic noon, supermassive black holes grew alongside the stellar populations. The two processes were linked. As galaxies formed, stars frantically, their central black holes fed equally frantically. Both stars and black holes competed for the same gas supply. In some cases, the black holes won. Their energy output became so intense that it heated surrounding gas beyond the temperature required for star formation. This shut down further stellar birth, quenching the galaxy. Webb observed galaxies frozen mid-quench, their outer regions still forming stars while their cores had gone dark. Cosmic noon revealed the universe at its most productive. After this epoch, star formation declined steadily. Galaxies consumed their gas supplies. Black hole feedback became more efficient at preventing new star formation. The universe entered a long, slow decline into its current state, where most galaxies form stars at modest rates or not at all. Understanding cosmic noon is critical because it shaped the universe we inhabit. The stars born then seeded the cosmos with heavy elements. They formed the first mature galaxies. They created the conditions for planets, chemistry, and eventually life. Half of existence traces its origin to this brief explosive epoch. But while Webb was revealing cosmic noon's secrets, it was simultaneously confirming something that threatened our entire cosmological framework. The universe is expanding. This is not a theory. It is an observed fact, measured countless times since Edwin Hubble first noticed it in 1929. Galaxies rush away from each other. Space itself stretches. The farther away a galaxy is, the faster it recedes. Astronomers measure expansion using the Hubble constant, a number that relates a galaxy's distance to its recession velocity. Knowing the Hubble constant tells you how fast the universe is expanding. It lets you calculate the universe's age. It determines the fate of cosmic expansion billions of years from now. There is just one problem. We cannot agree on what the Hubble constant actually is. Two different measurement methods give two incompatible answers. This discrepancy is called the Hubble tension. One method looks at the cosmic microwave background, the faint radiation left over from the Big Bang. This light comes from 380,000 years after creation, when the universe first became transparent. By analyzing tiny temperature fluctuations in this radiation, scientists can calculate how fast the universe was expanding at that early time. Using the standard cosmological model, they can project this early expansion rate forward to predict today's expansion rate. This method consistently gives a Hubble constant around 67 to 68 kilometers per second per megaparsec. That means, for every 3.3 million light-years of distance, space expands at an additional 67 kilometers per second. It is a precise number, calculated from exquisitely detailed cosmic microwave background maps. The second method uses direct observations of nearby galaxies. Astronomers measure distances to galaxies using specific types of stars called Cepheid variables. These stars pulse with a regular period directly related to their brightness. By comparing their apparent brightness to their actual luminosity, you can calculate their distance. Measuring many Cepheids in multiple galaxies builds up a cosmic distance ladder. This direct measurement method consistently gives a higher Hubble constant around 73 kilometers per second per megaparsec. The difference might sound small, 6 kilometers per second per megaparsec, but in cosmology, this discrepancy is enormous. The two methods should agree. They measure the same thing. Their disagreement suggests something fundamental is wrong. For years, scientists hoped the tension would resolve. Maybe the Hubble Space Telescope had systematic errors in its measurements. Maybe overlapping starlight confused the brightness measurements. Maybe dust dimmed some Cepheids more than expected. Each potential source of error was investigated, analyzed, and ruled out. Then Webb entered service. With its superior resolution and infrared sensitivity, Webb could observe Cepheid variables more clearly than any previous telescope. Adam Rees, a Nobel laureate who helped discover the universe's accelerating expansion, used Webb to observe over 1,000 Cepheid stars in 5 galaxies. Webb's measurements confirmed Hubble's results precisely. The Hubble constant, measured by direct observation, sat firmly around 73. The tension was not an instrument error. The discrepancy was real. Two valid measurement methods gave fundamentally different answers. This should not happen. When physicists disagree about a measurement, usually one method has a flaw. You test both methods carefully, find the error, correct it, and the measurements converge. The Hubble tension refuses to converge. Every refinement makes the two measurements more precise, but they remain stubbornly different. Xiang Li, a graduate student working on the Webb observations, described it as seeing the universe in high definition for the first time. The data was pristine, the measurements were unambiguous, the tension was confirmed beyond doubt. What does this mean? If both measurements are correct, then something about our understanding of cosmic expansion is wrong. The universe might not expand at a constant rate. Something might be influencing expansion that our models do not include. Dark energy, the mysterious force accelerating cosmic expansion, might behave differently than we thought. Mark Kamionkowski, a cosmologist studying the tension, suggested one possibility. Perhaps something was missing in our understanding of the early universe. Early dark energy, a hypothetical force that gave the young universe an extra push, might explain the discrepancy. Other possibilities include new particles, strange dark matter properties, or unknown forces active during the first moments after the Big Bang. The expansion mystery exposed a crack in cosmology's foundation. Our most successful theory, which explained everything from the Big Bang to galaxy formation to the universe's ultimate fate, produced contradictory predictions. Something fundamental needed revision, and it was about to get worse. For over a decade, The Hubble tension existed in scientific limbo. Yes, two measurement methods disagreed. But perhaps Hubble's Space Telescope had limitations that introduced subtle errors. Perhaps the cosmic microwave background analysis made assumptions that did not hold perfectly. Perhaps statistical fluctuations created an apparent discrepancy that further data would resolve. Scientists maintained hope that the tension was an artifact, not a real crisis. Tensions in physics sometimes disappear when measurements improve. Better instruments resolve ambiguities. More data clarifies confusion. The Hubble tension should have followed this pattern. It did not. Webb's independent confirmation of Hubble's measurements eliminated the last escape route. The tension was not an instrument error. It was not poor resolution. It was not statistical noise. Two fundamentally different approaches to measuring cosmic expansion gave genuinely different answers. Webb observed Cepheid variables in galaxies millions of light-years away, with clarity impossible for Hubble. The telescope's mirror, 6.5 meters across, collected far more light than Hubble's 2.4-meter mirror. Its infrared detectors saw through cosmic dust that blocked Hubble's view. The measurements were cleaner, sharper, more reliable. Every refinement confirmed the discrepancy. The Hubble constant, measured by observing nearby stars and galaxies, sat around 73. The Hubble constant calculated from the cosmic microwave background sat around 67. The gap was 6%. In normal science, 6% is enormous. It is the difference between correct and completely wrong. The implications were profound. If the cosmic microwave background method was right, then something about the local universe made it appear to expand faster than it actually did. If the direct measurement method was right, then something about the early universe made it expand slower than models predicted. Either way, our understanding was incomplete. Adam Rees stated the situation bluntly. The discrepancy between the observed expansion rate and the predictions of the standard model suggested our understanding of the universe might be incomplete. This was not speculation. This was the careful statement of a scientist confronting data that contradicted decades of established theory. The standard model of cosmology, lambda cold dark matter, had ruled since the late 1990s. It explained the cosmic microwave background patterns. It predicted the formation of large-scale cosmic structure. It described how galaxies evolved over billions of years. Hundreds of papers relied on it. Thousands of calculations assumed it. The entire architecture of modern cosmology rested on its foundations. The Hubble tension struck at those foundations. Lambda cold dark matter made specific predictions about cosmic expansion. Those predictions were wrong, not close, not slightly off, wrong by amounts that could not be attributed to measurement uncertainty. Some scientists proposed modifications to lambda cold dark matter. Perhaps dark energy, which drives cosmic acceleration, was not constant. Maybe its strength changed over time. This would affect expansion rates at different epochs, potentially reconciling the measurements. But every modification created new problems, requiring additional adjustments to preserve the model's other successes. Other scientists suggested the issue lay deeper. Maybe general relativity, Einstein's theory of gravity that underlies all cosmological models, needed revision at cosmic scales. Perhaps new forces existed beyond the standard model of particle physics. Maybe the universe contained extra dimensions that influenced expansion differently at different times. Each possibility opened unsettling prospects. Modifying general relativity meant revisiting every calculation in physics that assumed it was correct. Discovering new forces meant the standard model, which explained particle physics with exquisite precision, was incomplete. Adding extra dimensions required rethinking the fundamental nature of space and time. The Hubble tension demonstrated that something about our most basic understanding of reality was wrong. Either space expanded differently than we thought, or time flowed differently than we measured, or matter and energy interacted through mechanisms we had not discovered. No option was simple. No fix was obvious. Steven Finkelstein, studying the situation, noted that you needed overwhelming evidence to throw out a theory that had stood the test of time for so long. The tension was building toward that threshold. More observations would either resolve the crisis or confirm that cosmology required fundamental revision. Webb had eliminated the possibility of instrument error. The next question was whether our theory of the universe itself was fundamentally flawed. The answer emerging from the data looked increasingly like yes. In 1998, astronomers discovered something that should have been impossible. The universe's expansion was accelerating. Galaxies were flying apart faster and faster, driven by a mysterious force that pushed against gravity. Scientists called this force dark energy. Dark energy makes up 68% of the universe's total energy content. It permeates all of space. It does not clump or gather. It simply exists everywhere, exerting a constant pressure that drives cosmic expansion. Despite being the dominant component of reality, we have no idea what dark energy actually is. The simplest explanation is that dark energy represents the energy of empty space itself, what physicists call vacuum energy. Quantum mechanics predicts that even empty space contains energy from virtual particles constantly appearing and vanishing. If this vacuum energy remains constant over time, it would drive acceleration exactly as observed. This explanation has a catastrophic problem. When physicists calculate how much vacuum energy should exist based on quantum field theory, they get an answer that is 10 to the power of 120 times larger than observed. This is not slightly wrong. This is the worst prediction in the history of physics. Either our calculation is fundamentally broken, or dark energy is not vacuum energy. The Hubble tension suggested dark energy might be more complicated than a simple constant force. Perhaps its strength changed over cosmic history. Maybe it was stronger in the early universe, giving expansion an extra boost that our models did not account for. This hypothetical early dark energy could reconcile the different Hubble constant measurements. If early dark energy existed, it would have influenced cosmic history in specific ways. It would have changed how fast matter clumped together. It would have affected when the first stars ignited. It would have left signatures in the cosmic microwave background that could be detected if you knew what to look for. Scientists searched for these signatures. The cosmic microwave background data did not clearly support early dark energy. Some features in the data could be interpreted as consistent with it, but the evidence was not conclusive. This left early dark energy as a possibility, not a solution. Another idea suggested dark energy might interact with dark matter, the invisible mass that shapes cosmic structure. If dark energy and dark matter coupled together through unknown forces, this could create complicated effects on expansion rates at different epochs. But no theoretical framework predicted such coupling, and no observations directly indicated it existed. Some physicists proposed that dark energy was not a new force but a symptom of general relativity breaking down at cosmic scales. Perhaps Einstein's equations, which work perfectly in the solar system, required modification when applied to the entire universe. This idea led to theories called modified gravity, which tweaked gravitational laws to eliminate the need for dark energy. Modified gravity theories faced their own problems. They had to match all the successes of general relativity while also explaining cosmic acceleration. Most proposals either failed to match observations or required unnatural fine-tuning of parameters. None gained widespread acceptance. The most unsettling possibility was that dark energy genuinely was vacuum energy, and the calculation predicting the wrong value revealed a deep flaw in quantum field theory. This would mean our most successful physics theory, which explained particle interactions to 15 decimal places of precision, was built on incorrect foundations. Fixing it might require a completely new approach to quantum mechanics. Webb's observations did not directly measure dark energy, but by confirming the Hubble tension, the telescope demonstrated that our understanding of cosmic expansion had critical gaps. Dark energy, whatever it is, behaves in ways our models do not capture. Something about how it drives expansion depends on cosmic epoch, or location, or mechanisms we have not discovered. The question of dark energy goes beyond cosmology. It touches quantum physics, gravity theory, and the fundamental nature of space and time. Answering what dark energy is might require revising our entire framework for understanding reality. Webb had shown that this revision was not optional. The data demanded it, and the telescope was simultaneously discovering other problems with the universe's most fundamental components. The lambda in lambda-cold dark matter refers to the cosmological constant, Einstein's representation of dark energy. Einstein introduced it in 1917 to keep the universe static, then called it his greatest blunder after Hubble discovered cosmic expansion. Decades later, observations of accelerating expansion resurrected lambda, transforming it from a mistake into a cornerstone of cosmology. Lambda-cold dark matter, or LCDM, became the standard model of cosmology in the late 1990s. It describes a universe composed of 5% ordinary matter, 27% cold dark matter, and 68% dark energy, represented by lambda. This model successfully explained the cosmic microwave background, galaxy clustering, supernova observations, and countless other phenomena. LCDM makes precise predictions. Given the universe's composition and initial conditions, the model calculates exactly how structure should form over time, how quickly matter clumps, when the first stars ignite, how galaxies grow. These predictions matched observations beautifully for 2 decades. Then Webb started operating. The telescope's discovery of massive early galaxies directly contradicted LCDM predictions. According to the model, galaxies at 600 million years after the Big Bang should contain no more than 1 billion solar masses. Webb found galaxies 10 times more massive. LCDM predicted dim proto-galaxies. Webb found blazing stellar metropolises. The model also predicted that galaxy formation should be gradual. Dark matter halos should slowly accumulate mass over hundreds of millions of years. Gas should trickle in and form stars incrementally. Instead, Webb observed galaxies that assembled rapidly, forming most of their stars in sudden bursts, separated by just millions of years. Cold dark matter, the second component in LCDM, refers to dark matter particles that move slowly compared to light speed. These particles clump together efficiently under gravity, forming the scaffolding upon which galaxies build. Cold dark matter successfully explains large-scale cosmic structure, but Webb's observations suggested it might not explain small-scale galaxy properties. The overmassive black holes Webb discovered challenged LCDM's predictions about how black holes and galaxies co-evolve. The model assumes they grow together, maintaining specific mass ratios. Finding black holes that outweigh their galaxies by factors of 10 or more suggested either the model's assumptions were wrong or black holes formed through mechanisms LCDM did not include. The Hubble tension exposed another LCDM failure. The model calculated cosmic expansion based on early universe conditions and predicted today's expansion rate precisely. That prediction was wrong by 6%. In a model that worked correctly, such a large error should not exist. Either the input parameters were incorrect, or the model's equations did not capture reality. Scientists tried to modify LCDM to match observations while preserving its successes. Every modification created trade-offs. Adding early dark energy helped with the Hubble tension but required fine-tuning new parameters. Adjusting dark matter properties could match early galaxy masses, but disrupted predictions about large-scale structure. No simple fix worked. Some researchers proposed abandoning LCDM entirely. Perhaps the universe's composition was different than we thought. Maybe dark matter came in multiple types with different properties. Perhaps dark energy evolved over time rather than remaining constant. Each alternative model made its own predictions that could be tested against observations. The problem ran deeper than just tweaking parameters. LCDM rested on fundamental assumptions about physics. It assumed general relativity was correct. It assumed the universe was homogeneous and isotropic at large scales. It assumed the laws of physics were the same everywhere and at all times. If Webb's observations proved irreconcilable with LCDM, then one of these assumptions might be wrong. Challenging general relativity seemed extreme. Einstein's theory had passed every experimental test for over a century. GPS satellites relied on its predictions to function. Gravitational waves, detected in 2015, matched its equations perfectly. Yet cosmology applied general relativity to the entire universe over billions of years. Perhaps at these scales, the theory required modification. Questioning cosmic homogeneity was equally radical. All observations suggested the universe looked roughly the same in all directions at large scales. But perhaps the early universe had more structure than we realized. Maybe regions of higher density existed where galaxies could form faster. This would require rethinking how the Big Bang distributed matter. The lambda problem exemplified a broader crisis. Our most successful cosmological model, validated by decades of observations, was producing predictions that Webb proved false. The model was not completely wrong. It still explained many phenomena correctly, but it was incomplete in fundamental ways that demanded new physics. The situation resembled the early 1900s, when classical physics faced anomalies that quantum mechanics eventually resolved. Cosmology now faced its own anomalies. Resolution would require either modifying LCDM significantly or developing an entirely new framework for understanding cosmic evolution. Webb was not done exposing problems. The telescope's observations of galaxy shapes revealed another challenge to our understanding of dark matter itself. Galaxies in the nearby universe have familiar shapes. Spirals like the Milky Way spin with elegant arms wound around central bulges. Ellipticals glow as featureless, smooth blobs of stars. Irregulars display chaotic structures resulting from collisions and mergers. These shapes reflect billions of years of evolution and countless gravitational interactions. When Webb looked at galaxies in the early universe, it found shapes that should not exist. Many young galaxies appeared stretched, elongated into filaments spanning tens of thousands of light years. These structures were not rare exceptions. They appeared commonly at redshifts corresponding to 1 billion years or less after the Big Bang. Cold dark matter theory predicts that galaxies should form roughly spherical at first, then flatten into disks as they acquire angular momentum from their surroundings. This process should take hundreds of millions of years. Young galaxies should be compact blobs, not elongated strands. The elongated shapes suggested gas was flowing into these galaxies along preferred directions rather than from all sides equally. This indicated that dark matter halos, the invisible gravitational frameworks around which galaxies form, had specific orientations and shapes from very early times. Cold dark matter simulations typically produce halos that are somewhat elongated but not extremely so. The most extreme theoretical predictions suggested axis ratios around 2:1, meaning a halo might be twice as long as it is wide. Webb found galaxies with axis ratios exceeding 3:1, far more elongated than cold dark matter alone could produce. Researchers ran new simulations testing different dark matter models. Instead of cold dark matter, which consists of slow-moving particles, they tried warm dark matter, which consists of faster-moving particles. Warm dark matter particles move too quickly to clump as efficiently as cold dark matter. This creates smoother cosmic structures with less small-scale clumping. The simulations showed that warm dark matter naturally produced elongated structures in the early universe. Cosmic filaments, the vast strands of matter connecting galaxy clusters, formed more smoothly in warm, dark matter model. Gas flowed along these filaments steadily, building galaxies that inherited the filament's elongated shape. Another alternative was wave dark matter, which treats dark matter as extremely light particles that behave like quantum waves rather than classical particles. These waves interfere with each other, creating patterns that influence structure formation differently than particle dark matter. Wave dark matter also predicted more elongated early structures than cold dark matter. The observation of elongated galaxies provided potential evidence for alternatives to cold dark matter. This was significant because cold dark matter had dominated cosmology for decades despite having no direct detection. Particle physicists have searched for cold dark matter particles in underground detectors for 40 years without finding them. Discovering that warm or wave dark matter matched observations better would represent a major shift in understanding. The implications extended beyond galaxy shapes. Different dark matter properties would affect everything from galaxy formation rates to cosmic structure evolution to the behavior of dark matter in galaxy clusters. Confirming warm or wave dark matter would require revising countless calculations and predictions built on cold dark matter assumptions. Not everyone agreed that the elongated galaxies proved cold dark matter was wrong. Some researchers suggested that gas dynamics, not dark matter properties, produced the shapes. If gas cooled and collapsed along specific directions due to the orientation of nearby structures, it might create elongated galaxies regardless of dark matter type. Distinguishing between these possibilities required more observations. Scientists needed to measure not just galaxy shapes but also their internal kinematics, how gas and stars moved within them. They needed to observe larger samples to establish statistical significance. They needed to compare observations across different cosmic epochs to see how shapes evolved. Webb provided some of this data, revealing that elongated galaxies existed primarily in the first billion years of cosmic history. By cosmic noon, most galaxies had settled into more familiar disk or elliptical shapes. This time, evolution suggested that whatever process created the elongation operated early but ceased as the universe aged. The elongated galaxy discovery demonstrated that even our understanding of dark matter, which we had never directly observed, might require fundamental revision. If the shapes were truly incompatible with cold dark matter, then decades of theory and simulation work would need reconsideration. But while astronomers debated dark matter properties, Webb had found an individual object so extreme that it forced scientists to abandon their models completely and start over. In July 2024, astronomers identified an object that stopped them cold. They were examining little red dots from the Rubier survey, the Red Unknown's bright infrared extragalactic survey. When they encountered something with properties so extreme they knew immediately it was special, they called it the cliff. The cliff existed 12 billion light-years away, meaning its light showed the universe as it appeared just 1.6 billion years after the Big Bang. At first glance, it resembled other little red dots, a small red object glowing brightly in Webb's deep images. Then scientists examined its spectrum, the breakdown of light into individual wavelengths. The spectrum revealed a feature called the Balmer break, a sharp jump in brightness at a specific wavelength caused by hydrogen atoms transitioning between energy levels. Every star and galaxy shows some Balmer break. The cliff's Balmer break was not normal. It was nearly vertical, an almost discontinuous leap in brightness that no combination of ordinary stars could produce. Anna de Graaf, researcher at the Max Planck Institute and lead author on the cliff study, stated that its extreme properties forced the team to go back to the drawing board and come up with entirely new models. Nothing in their toolkit of galaxy formation theory could explain what they were seeing. The spectrum showed other unusual features. Strong emission lines indicated gas heated to over 10,000 degrees, moving at speeds exceeding 2,000 miles per second. These velocities suggested violent processes, matter being accelerated by tremendous gravitational or pressure forces. Yet the object remained compact, less than 1,000 light-years across. Most perplexing, was the combination of features. The sharp Balmer break suggested cool, dense gas, like the atmospheres of old stars. But the emission lines suggested hot, sparse gas, like the environment around feeding black holes. These conditions should not coexist. Cool, dense gas and hot, sparse gas occupy different physical regimes. Joel Lager, researcher at Penn State working on the analysis, realized they needed a fundamentally new type of object to explain the cliff. Not a galaxy, not a quasar, not a star cluster. Something that had never been seen before because it only existed in the early universe under conditions that no longer occur. The team proposed that the cliff was a black hole star, a supermassive black hole surrounded by an extremely dense atmosphere of gas that glowed like a single gigantic stellar photosphere. The black hole would provide the energy through gravitational accretion. The dense envelope would produce the spectral features. The system would appear as one enormous luminous object. This model explained everything. The sharp Balmer break came from the dense atmosphere. The emission lines came from the inner regions where gas spiraled toward the black hole. The compactness reflected the fact that this was essentially a single object, not a collection of billions of stars. The brightness came from super Eddington accretion, the black hole feeding faster than normal limits allowed. The cliff's black hole mass was estimated at several 100 million solar masses. Its host galaxy, the faint glow of normal stars surrounding the black hole star, contained less than 1 billion solar masses. The black hole outweighed its galaxy, another overmassive system, but more extreme than previous examples. If the cliff truly was a black hole star, it represented a missing link in understanding how supermassive black holes formed. These objects could be the infancy stage of black holes, the rapid growth phase before they settled into their galaxies as mature quasars. This would explain how black holes reached billions of solar masses so quickly in the early universe. The discovery had broader implications. If black hole stars existed, they might be common in the early universe. Many little red dots might be examples of this phenomenon. Scientists would need to reanalyze all previous observations of early galaxies to determine which were genuine galaxies and which were black hole stars masquerading as galaxies. The cliff also suggested that the early universe was more exotic than cosmologists had imagined. It was not just a younger version of the modern universe with the same objects at earlier stages. It contained object types that no longer exist, phenomena that could only occur under the extreme conditions of cosmic dawn. Lager described the cliff as the best evidence to date that at least some little red dots were not ultra-dense massive galaxies, but were instead powered by a central ionizing source embedded in dense absorbing gas. This was not speculation. The spectral evidence was clear. The modeling was rigorous. The conclusion was firm. But the cliff was not the only object showing extreme black hole activity. Webb was discovering that the early universe was full of black holes, feeding at impossible rates. Black holes have an appetite limit. As matter spirals into a black hole, friction heats the infalling material to millions of degrees. This hot gas radiates intensely, producing so much light that the radiation pressure pushes against new material trying to fall in. This balance between gravity pulling inward and radiation pushing outward defines the Eddington limit, the maximum rate at which a black hole can grow. The Eddington limit says a black hole of 1 million solar masses can accrete no more than about 10 solar masses per year. Try to exceed this rate, and radiation pressure becomes so strong that it blows away the infalling matter. The black hole essentially chokes on its own light, unable to swallow material fast enough. Webb found black holes that violated this limit by factors of 10 or more. They were feeding at rates that should be physically impossible, consuming hundreds of solar masses per year while radiating with luminosities that should have halted all accretion. The laws of physics said this could not happen. The observations said it was happening anyway. In the galaxy Virgil, the supermassive black hole consumed matter at 8 times the Eddington rate. The black hole was growing so fast that it added mass equivalent to our entire stellar mass every million years. At this rate, a black hole could reach billions of solar masses in just hundreds of millions of years, explaining how such massive black holes appeared so early in cosmic history. But how could black holes exceed the Eddington limit? Several mechanisms had been proposed theoretically. One possibility was that matter fell in from preferred directions rather than spherically. If gas streamed in along narrow channels, radiation could escape through other directions without impeding the inflow. This allowed higher accretion rates while still radiating immense energy. Another mechanism involved magnetic fields. Strong magnetic fields could confine the accretion flow, preventing radiation pressure from disrupting it. The magnetic field would act like a cage, forcing matter inward despite the outward push from radiation. Simulations showed this could increase sustainable accretion rates by factors of 5 to 10. A third possibility was that these black holes formed already massive through direct collapse mechanisms. Instead of starting as 10 solar mass stellar remnants, perhaps they began as thousands or millions of solar masses when they first formed. This would give them a head start, requiring less super Eddington feeding to reach observed masses. The feeding frenzy extended beyond individual objects. Webb observed entire populations of actively feeding black holes during cosmic noon. Surveys revealed that between 10 and 30% of massive galaxies at that epoch hosted rapidly accreting black holes. This fraction was much higher than in the modern universe, where only 1 to 2% of galaxies show active black hole feeding. The cosmic noon feeding frenzy explained why supermassive black holes exist at all. If black holes only fed at Eddington limited rates, they would need tens of billions of years to reach billions of solar masses. The universe is only 13.8 billion years old. Super Eddington feeding during the first few billion years allowed black holes to reach their current masses in the available time. But the feeding came at a cost to their host galaxies. Energy from the accreting black holes heated surrounding gas, preventing it from cooling and forming stars. This negative feedback gradually shut down star formation in galaxies, transforming them from vibrant stellar factories into quiet elliptical galaxies full of old red stars. Webb captured this process in action. The telescope observed galaxies where the center had stopped forming stars, while outer regions continued. The central quenching corresponded precisely with evidence of strong black hole activity. The black hole was killing its host galaxy by heating its gas supply beyond the point where stars could form. This relationship between black holes and star formation explained a long-standing mystery in cosmology. Why do massive elliptical galaxies contain so few young stars? Why did cosmic star formation decline after cosmic noon? Black hole feedback provided the answer. Once black holes grew massive enough, their energy output shut down further growth, both their own and their galaxies. The black hole feeding frenzy revealed the early universe as a violent place where matter flowed not in steady streams, but in torrents, where black holes gorged themselves on gas at impossible rates, where the energy released shaped the evolution of entire galaxies. This was not the gradual, orderly universe that models predicted. This was chaos restrained only by the laws of physics, and even those laws were being pushed to their breaking points. And some of these feeding black holes were wrapped in so much dust that previous telescopes could not see them at all. Cosmic dust is not like house dust. It consists of tiny grains, microscopic particles of carbon, silicon, oxygen, and other elements forged in stars and expelled through stellar winds or supernova explosions. These grains are smaller than the wavelength of visible light, perfect for absorbing and scattering blue and ultraviolet radiation. When dust accumulates around galaxies and black holes, it acts like a curtain, hiding what lies beneath from optical telescopes. The Hubble Space Telescope, optimized for visible and ultraviolet light, could see through thin dust, but struggled with heavily obscured objects. Much of the early universe's most active regions remained hidden. Webb's infrared vision changed this. Dust that blocks visible light is transparent to infrared radiation. Webb could peer through cosmic curtains that stopped previous telescopes, revealing hidden populations of dust-shrouded galaxies and black holes that had been missed by decades of observations. The mega survey, focused on cosmic noon, found that most star formation at that epoch occurred in dust-shrouded galaxies. These objects appeared faint or invisible to Hubble, but blazed in Webb's mid-infrared images. The telescope revealed that previous surveys had missed half the star formation activity in the early universe simply because dust hid it. The extended Groth strip observations showed multiple galaxies wrapped in so much dust that their starlight was attenuated by factors of 100 or more. Only 1% of their light escaped in visible wavelengths. The remaining 99% was absorbed by dust and re-emitted as infrared radiation. Without infrared-sensitive instruments, these galaxies would remain invisible. Some dust-shrouded monsters hosted both intense star formation and rapidly feeding black holes. The dust itself was produced by massive stars, which live only a few million years before exploding as supernovae. Finding heavy dust around early galaxies confirmed that these systems had already cycled through multiple generations of stars, creating and dispersing the heavy elements that form the dust grains. The dust distribution around galaxies was not uniform. It clumped in specific regions, particularly in the central bulges where star formation was most intense. This created complicated patterns where some parts of a galaxy remained visible while others were completely obscured. Webb's high resolution allowed astronomers to map these dust patterns in detail, revealing complex structures that lower resolution telescopes saw as uniform blobs. One particular category of objects, the infrared luminous galaxies, emitted 90% of their energy in infrared wavelengths. These galaxies were invisible to optical surveys but dominated the cosmic infrared background, the collective glow of all distant galaxies added together. Webb revealed them as compact, dust-enshrouded systems undergoing intense starbursts. The dust itself provided clues about galaxy evolution. Different dust compositions produced different infrared spectra. Silicate dust, formed from silicon and oxygen, created distinct emission features. Carbon dust, produced in carbon-rich stars, showed different patterns. By analyzing these spectral signatures, astronomers could determine what types of stars produced the dust and how long ago those stars formed. Some dust-shrouded objects showed temperatures far higher than normal star formation could produce. The dust was heated to over 1,000 degrees, hot enough that it glowed brightly in mid-infrared wavelengths. This extreme heating required an additional energy source beyond stars, likely a feeding supermassive black hole hidden within the dust. The discovery of these dust-shrouded monsters forced astronomers to revise their understanding of cosmic history. Previous calculations of star formation rates were wrong because they missed the contribution from heavily obscured galaxies. Previous black hole demographics were incomplete because dust hid many actively feeding systems. Entire populations of objects existed that earlier telescopes could not detect. Webb's infrared capabilities revealed that the early universe was not only more massive and more active than we thought, but also more obscured. Much of cosmic evolution happened behind dust veils that only now were being lifted. Each object Webb uncovered raised new questions about how much else remained hidden. And sometimes, the dust concealed not just active galaxies, but galaxies in the violent throes of merging together. In the modern universe, galaxy mergers are rare, spectacular events. When two galaxies collide, they take hundreds of millions of years to fully merge, their stars mostly passing through each other like ghosts, while their gas clouds slam together in shockwaves that ignite intense star formation. In the early universe, mergers were not rare, they were the norm. Webb's observations revealed that most young galaxies were undergoing mergers or had recently merged. The early universe was a place of constant collisions. a demolition derby of galaxies smashing together in violent interactions. The Canuck survey, the Canadian NIRIS Unbiased Cluster Survey, captured a pair of galaxies just beginning to merge 7 billion years ago during cosmic noon. One galaxy appeared blue and face-on, full of young, hot stars. The other appeared red and edge-on, wrapped in dust. They were locked in each other's gravitational embrace, destined to combine into a single larger galaxy. What made this observation special was a lucky alignment. A massive galaxy cluster between Earth and the merging pair acted as a gravitational lens, magnifying and brightening the distant galaxies. This particular lens configuration, called a hyperbolic umbilic lens, was extremely rare. Only 3 or 4 examples were known in the entire observable universe. The gravitational lens produced multiple images of the merging galaxies, each showing different regions at different magnifications. This allowed astronomers to study star formation rates across both galaxies in unprecedented detail. They measured how star formation varied between the central regions and the outer disks, between the collision interface and the undisturbed areas. The results showed that star formation spiked violently where the 2 galaxies' gas clouds collided. At these collision points, gas compressed by factors of 100 or more, triggering immediate star formation at rates exceeding 1,000 solar masses per year per square kiloparsec. This was thousands of times higher than star formation rates in peaceful galaxies. Vicente Estrada Carpenter, lead author on the study, developed a new method to measure star formation on different timescales. Ultraviolet light traces stars formed over the past 100 million years. Hydrogen alpha emission traces stars formed in just the past 10 million years. Comparing these measurements revealed how star formation rates changed as the merger progressed. The technique showed that mergers proceeded in bursts. Gas compression would trigger intense star formation for a few million years. Feedback from those new stars would heat and disperse the remaining gas, shutting down star formation. Eventually, the gas would cool and collapse again, triggering another burst. This cycle repeated multiple times during a single merger. The violence of these collisions had profound effects on galaxy structure. Simulations showed that gas driven toward the center by merger dynamics could feed the central black hole, causing it to activate and grow. This explained why many active black holes existed in galaxies showing signs of recent mergers. Mergers also destroyed ordered rotation. Before collision, both galaxies rotated systematically, like water swirling down a drain. After collision, their motions became chaotic. Gas moved in random directions. Stars orbited on tilted, eccentric paths. It took hundreds of millions of years for this chaos to settle into a new, orderly structure. JWST observations of earlier galaxies, at redshifts corresponding to less than 1 billion years after the Big Bang, showed even more extreme chaos. These galaxies had not yet settled into disks. They consisted of clumps and streams of gas, fragments that were themselves merging together. The distinction between merger and formation blurred because galaxies were being assembled from smaller pieces constantly. Lola Danhive, studying these chaotic early systems, found huge variation in their properties. Some were beginning to settle into ordered rotation. Most remained turbulent, with gas puffed up and moving in all directions. This turbulence resulted from ongoing mergers and vigorous star formation that stirred gas violently. The merger violence explained several puzzles. It accounted for why early galaxies were so massive. Each merger added mass from both progenitors. It explained why black holes grew so quickly. Mergers funneled gas toward the centers where black holes fed. It explained why many early galaxies showed unusual shapes. They were caught mid-collision, not yet settled into final configurations. Chris Hayward, studying galaxy collisions, noted that the violence peaked during cosmic noon and declined afterward. As the universe expanded and matter spread out, galaxies became more isolated. Merger rates dropped. By the current epoch, Massive galaxy mergers are rare events rather than the constant background state. But merger violence had lasting consequences. The energy released during collisions heated intergalactic gas, making it harder for future generations of galaxies to form. The mixing of gas from different galaxies enriched the universe with heavy elements. The central black holes that grew during mergers became the seeds of present-day supermassive black holes. Galaxy merger violence shaped the universe we inhabit. Every massive elliptical galaxy today formed through mergers of smaller spirals. Every supermassive black hole grew fat on gas, channeled by merger dynamics. The chaos of the early universe was not a bug in cosmic evolution. It was the feature that built everything. Star formation cannot continue forever. Galaxies eventually run out of gas, their fuel supply exhausted, but many galaxies stop forming stars long before they run out of material. Something shuts them down prematurely. Astronomers call this quenching. For decades, the mechanism behind quenching remained mysterious. Theories suggested stellar winds might blow gas away. Supernova explosions might heat gas too hot to collapse. Galaxy mergers might disrupt star-forming regions. Each process contributed, but none fully explained why massive galaxies stopped forming stars while smaller galaxies continued. Webb provided the answer. The telescope observed over 100 galaxies during cosmic noon, capturing them at the peak epoch of both star formation and black hole growth. The observations revealed a clear pattern. Galaxies with actively feeding black holes showed suppressed star formation in their central regions, even while their outer areas continued producing stars. Rebecca Davies, leading the research from Swinburne University, explained that supermassive black hole activity generated powerful outflows. Gas heated by the accreting black hole rushed outward at speeds exceeding 1,000 miles per second. These winds swept through the galaxy, colliding with cool molecular clouds where stars would normally form. The collision between hot outflows and cold clouds had devastating effects on star formation. The outflows heated the clouds from a few tens of degrees to thousands of degrees. At these temperatures, gas pressure overwhelmed gravity. The clouds dispersed rather than collapsing. Star formation ceased. Webb's near-infrared spectrograph captured the outflows directly. The instrument detected absorption lines from neutral gas, moving at extreme velocities away from galactic centers. These outflows carried mass equal to hundreds of times our stellar mass, enough gas to form billions of stars if it had remained in the galaxy. The quenching proceeded from the inside out. Black hole feedback first shut down star formation in the central kiloparsec, the core region surrounding the black hole. This created what astronomers call a post-starburst signature, evidence of recent vigorous star formation that had abruptly stopped. As the black hole continued feeding, the quenched region expanded outward, gradually encompassing more of the galaxy. Not all gas escaped entirely. Some outflows reached maximum height above the galactic disk, slowed by gravity, and fell back down. This recycled gas eventually cooled and could resume forming stars. But the process took hundreds of millions of years. During that time, the galaxy remained quenched. The efficiency of quenching depended on black hole mass. More massive black holes generated more energetic outflows that quenched larger regions. This explained why the most massive galaxies contained the oldest stellar populations. Their oversized black holes had shut down star formation billions of years ago. Davies noted that direct evidence for black hole quenching had been lacking until now. Astronomers could see the effects, galaxies with dead cores, but could not directly observe the mechanism. Webb's sensitivity to outflow signatures provided the smoking gun, catching black holes in the act of killing their host galaxies. The quenching effect resolved a major puzzle in galaxy evolution. Why did cosmic star formation decline after cosmic noon? Because black holes grew massive enough to shut it down. Why do massive elliptical galaxies contain only old stars? Because their central black holes quenched star formation billions of years ago. Why does the modern universe form stars at much lower rates than the early universe? because most large galaxies have been quenched. This discovery revealed black holes as sculptors of cosmic evolution. They did not just passively grow within galaxies, they actively shaped galaxy properties, determining when star formation ended and transforming vibrant spirals into quiet ellipticals. But some black holes were so dominant that their galaxies barely existed at all. In 2025, astronomers identified an object that challenged the very definition of a galaxy. Designated Abell 2744-QS01, it consisted of a supermassive black hole surrounded by almost no stars. The black hole blazed with the light of billions of stellar fires. The stellar population around it was nearly absent. Scientists called it a naked black hole, a central engine exposed without the usual galactic clothing of stars and gas. The object existed just under 1 billion years after the Big Bang, during the epoch when galaxies and black holes supposedly grew together. Somehow, this black hole had grown to massive size without building a substantial galaxy around it. The black hole's mass exceeded several 100 million solar masses. The surrounding stellar mass measured less than 1 billion solar masses, possibly far less. Analysis suggested the galaxy contained perhaps 1/10 the stars expected for a black hole of this mass. The black hole outweighed its galaxy by ratios exceeding anything previously observed. How could such an object form? Standard galaxy formation theory predicted that black holes and galaxies grew together through a self-regulating cycle. Gas fell into the dark matter halo. Some gas formed stars. Some gas fed the central black hole. Black hole feedback eventually limited both processes, maintaining the mass ratio observed in normal galaxies. Naked black holes broke this cycle. Either the black hole formed first and grew rapidly before the galaxy assembled, or the galaxy formed but was later stripped away, leaving only the black hole core. Both scenarios required conditions that standard models did not predict. One possibility was that naked black holes formed from direct collapse. Under specific conditions in the early universe, massive gas clouds could collapse directly into black holes without first forming stars. These direct collapse black holes would begin with masses of 10,000 to 100,000 times our solar mass, giving them a huge head start over black holes formed from stellar remnants. With this initial advantage, direct collapse black holes could grow to supermassive sizes quickly by feeding voraciously on surrounding gas. If the feeding rate exceeded galaxy formation rate, the black hole would dominate before a substantial stellar population assembled. Another explanation involved environmental effects. If a naked black hole existed in a region with strong tidal forces from nearby galaxies or clusters, those forces could strip away stars while leaving the central black hole relatively unaffected. Stars respond to tidal forces because they have finite size. A compact black hole would resist stripping more effectively than diffuse stellar populations. Recent simulations of overmassive black holes at cosmic noon suggested this stripping mechanism might be common. 12 low-mass galaxies, observed at redshifts between 1 and 3, all showed black holes far too massive for their stellar content. The researchers proposed that tidal stripping removed stars, leaving overmassive black hole cores. Naked black holes had profound implications for understanding the relationship between black holes and galaxies. If black holes could exist without galaxies, then black holes were not simply byproducts of galaxy formation. They were independent entities that could form through different channels and under different conditions. The discovery also raised questions about what we call a galaxy. If an object consists primarily of a black hole with minimal stars, is it still a galaxy? Or is it something else, a black hole with accessories? Definitions matter in science because they shape how we categorize and understand phenomena. Several other candidates for naked black holes appeared in Webb surveys. These objects showed similar properties: extremely luminous, very compact, with spectral signatures indicating powerful black hole accretion but weak stellar populations. As observations continued, the list grew. Finding naked black holes in the early universe suggested the black hole population was more diverse than we realized. Some black holes grew within galaxies as expected. Others followed different evolutionary paths, achieving dominance over their surroundings or existing in isolation. The early universe hosted a zoo of black hole configurations, not the uniform population that models predicted. These naked monsters would not remain naked forever. Eventually, gas would continue falling into their dark matter halos, forming new generations of stars. Over billions of years, they would acquire normal stellar populations and become regular galaxies, but their black holes would always remain overmassive, a fossil record of their unusual origins. The discovery of naked black holes added another item to the growing list of early universe phenomena that cosmological models failed to predict. Each new object class challenged assumptions we thought were secure. When the James Webb Space Telescope sent back its first deep field images in July 2022, astronomers expected to confirm existing theories about the early universe. Instead, they found galaxies that were so massive, so mature, so impossible, according to prevailing models, that someone needed a name for them. Ivo Labb, an astronomer at Swinburne University in Australia, who identified 6 of the most extreme examples, coined the term unofficially. He called them universe breakers. The name spread quickly through the astronomical community because it captured the essence of the problem. These objects broke the universe as we understood it. The term was not hyperbole. The standard model of cosmology, lambda, cold, dark matter, made specific predictions about galaxy masses at different epochs. These predictions were not vague estimates. They were precise calculations based on well-tested physics. For galaxies at 600 to 800 million years after the Big Bang, the maximum stellar mass should not exceed 1 billion solar masses. The 6 universe breakers weighed between 10 billion and 30 billion solar masses each. They exceeded predictions by factors of 10 to 30. This was not a small discrepancy. This was not measurement uncertainty. This was a fundamental contradiction between theory and observation. Scientists debated whether the name was appropriate. Some argued it was too dramatic, that the term implied cosmology was completely wrong when perhaps only minor adjustments were needed. Others embraced it, noting that minor adjustments could not fix errors this large. The debate over terminology reflected deeper tensions within the astronomical community. When observations contradict established theory, 2 reactions are possible. Either the observations are wrong, or the theory is wrong. For a century, when new observations seemed impossible, astronomers typically found that measurement errors or misinterpretations explained the discrepancy. Universe breakers were different. Multiple independent teams confirmed them. Different instruments observed them. Various analysis techniques all returned similar results. The observations were solid. If universe breakers were wrong, then something fundamental about how we measure galaxy masses and distances had to be broken. As more data accumulated, some universe breakers proved less extreme than initially thought. Katherine Chorowski and colleagues showed that supermassive black holes made several galaxies appear more massive than they actually were. Black hole light contaminated the measurements, inflating the apparent stellar mass. This resolved some cases, but not all. Even after accounting for black hole contamination, multiple galaxies remained too massive for their age. These were genuine universe breakers, not measurement artifacts. The term stuck because it described a real phenomenon, not a mistake. The universe breakers sparked the most intense cosmological controversy in decades. Papers appeared arguing that lambda, cold, dark matter, needed modification. Other papers defended the model, proposing that faster star formation in the early universe could explain the massive galaxies without changing fundamental physics. Some researchers suggested the universe breakers indicated we had misunderstood the Big Bang timeline itself. Perhaps the universe was older than 13.8 billion years. This would give galaxies more time to grow massive. But this proposal contradicted precise measurements of the cosmic microwave background that established the universe's age independently. Others proposed that the initial conditions after the Big Bang were different than we thought. Maybe some regions had higher matter density, allowing faster galaxy formation, but this contradicted observations of cosmic homogeneity at large scales. The naming of universe breakers marked a turning point. It acknowledged publicly that observations had exceeded the bounds of established theory. It admitted that cosmology faced a genuine crisis, not just a puzzle requiring tweaks. The name became a rallying point for those arguing that fundamental revision was necessary. Mike Boylan-Colchin, analyzing the situation, stated that if the masses were right, we were in uncharted territory. We would require something very new about galaxy formation, or a modification to cosmology. The universe breakers had forced this recognition, but naming the problem was just the first step. Understanding why these objects existed required finding more of them and characterizing their properties in detail. After identifying the first universe breakers, scientists launched systematic surveys to find more. They needed to determine whether these objects were rare anomalies or common features of the early universe. The answer would determine how seriously cosmology needed revision. Webb observed multiple deep fields, regions of sky where it stared for hundreds of hours, collecting light from the faintest, most distant objects. Teams at the University of Missouri, Colby College, and other institutions compiled datasets from these surveys, searching for objects with the characteristic properties of universe breakers. Bangzhang Yu and Haojing Yan at the University of Missouri focused on a specific category called dropouts. These objects appear bright at long wavelengths but disappear completely at short wavelengths. The sudden dropout indicates that we are seeing the light redshifted past a specific threshold, telling us the object's distance. Using Webb's NIRCam instrument, the Missouri team identified 300 very bright dropouts at extreme distances. These objects existed in the first billion years after the Big Bang, the epoch where universe breakers resided. Most showed the same troubling properties: too bright, too massive, too mature for their age. 300 was not a small number. It indicated that universe breakers were not rare flukes. They represented a significant population, perhaps 10 to 20% of all massive galaxies at that epoch. Any model of galaxy formation had to explain not just a handful of weird objects, but an entire population. Dale Kuchevsky at Colby College led a parallel effort focused on little red dots. His team compiled one of the largest samples of these objects, identifying 341 examples across multiple surveys. Most existed at redshifts corresponding to the same early epoch as the bright dropouts. The overlap between populations was striking. Many little red dots were also bright dropouts. Many showed signs of being universe breakers, hosting masses far exceeding predictions. The different names describe different aspects of the same underlying phenomenon. The early universe contained a large population of objects that should not exist according to standard models. Characterizing 300 objects required enormous effort. Each needed spectroscopic follow-up to confirm its distance and measure its properties precisely. Each needed detailed modeling to determine stellar mass, age, and star formation history. Each needed careful analysis to distinguish genuine galaxy mass from black hole contamination. The spectroscopic campaigns revealed diversity within the population. Some universe breakers were genuine galaxies packed with stars. Others were black hole stars, their light dominated by central black holes. Some showed signs of recent mergers. Others appeared surprisingly isolated. The population was not uniform. Despite the diversity, common patterns emerged. Most universe breakers existed in the first 800 million years after the Big Bang. Their numbers declined sharply at later times. By cosmic noon, 2 to 3 billion years after the Big Bang, few universe breakers remained. Whatever process created them operated early but ceased as the universe aged. Temperature measurements showed that many contained old stellar populations, red stars, which form from the evolution of hotter stars, appeared commonly. This confirmed that these were not simply young galaxies caught during an initial burst of star formation. They were mature systems containing multiple stellar generations. Chemical abundance measurements detected heavy elements. Carbon, oxygen, nitrogen, and iron appeared in quantities indicating that supernovae had already enriched the galactic gas. This meant at least one complete stellar generation had formed, evolved, and died before the galaxies were observed. The 300 universe breakers collectively represented the most serious challenge to cosmology in decades. Explaining one or two weird objects could be dismissed as rare outliers. Explaining hundreds required rethinking fundamental aspects of cosmic evolution. Stephen Finkelstein, studying the implications, noted that there was still a sense of intrigue because not everything was fully understood. The universe breakers had revealed gaps in our knowledge but had not yet provided clear answers about what was wrong. The data continued accumulating. More surveys, more objects. The population grew beyond 300. Each new discovery refined understanding but also raised new questions. The early universe was proving far stranger and more complex than anyone anticipated, and what these discoveries collectively meant for our understanding of reality was becoming increasingly clear. The standard model of cosmology is not a guess. It rests on decades of observations, hundreds of scientific papers, and thousands of hours of telescope time. Lambda, cold, dark matter, explains the cosmic microwave background patterns to exquisite precision. It predicts large-scale structure formation accurately. It describes cosmic expansion history correctly. It has survived every test thrown at it for 25 years. Webb's discoveries threatened to topple it, not because of a single anomaly, but because of accumulation of problems that could not be explained away. The massive early galaxies, the overmassive black holes, the Hubble tension, the elongated galaxy shapes. Each problem individually might be resolved with minor model adjustments. Together, they suggested something fundamental was wrong. The crisis centered on the cold dark matter component. This hypothetical substance makes up 85% of the universe's matter but has never been directly detected. Particle physicists have searched for cold dark matter candidates for 40 years without success. Underground detectors, particle colliders, and astrophysical searches have all come up empty. Lambda cold dark matter predicts that cold dark matter clumps hierarchically. Small halos form first. They merge to create larger halos. Galaxies grow gradually within these halos over billions of years. This bottom-up assembly process produces specific predictions about galaxy masses at different cosmic epochs. Webb's universe breakers contradicted these predictions. Galaxies appeared too massive too quickly, suggesting either cold dark matter clumps faster than models allow, or galaxy formation is more efficient than physics permits, or the initial conditions were different than we thought. The elongated galaxy shapes challenged cold dark matter from another direction. Cold dark matter simulations produce halos with specific axis ratios and angular momentum distributions. The observed shapes exceeded these predictions, suggesting either warm dark matter, wave dark matter, or some other modification was necessary. The Hubble tension struck at the lambda component. Dark energy, represented by Einstein's cosmological constant, should be perfectly uniform across space and constant over time. If it is, then cosmic expansion should proceed at predictable rates. The tension shows predictions fail, implying dark energy is more complicated than a simple constant. Some scientists proposed abandoning lambda cold dark matter entirely. Perhaps the universe's composition was fundamentally different. Maybe dark matter came in multiple types. Maybe dark energy evolved over time. Maybe both needed replacement with entirely new concepts. Others argued for incremental modifications. Add early dark energy to fix the Hubble tension. Adjust star formation efficiency to match early galaxy masses. Include additional physics in simulations to produce elongated shapes. Patch each problem individually while preserving the model's overall structure. The debate grew heated at scientific conferences. Defenders of lambda-cold dark matter argued that the model had too many successes to abandon based on preliminary data from a new telescope. Critics countered that the problems were too severe to ignore, that incremental patches were band-aids on a fundamentally flawed framework. Adam Rees, whose work confirmed the Hubble tension, stated that the discrepancy suggested our understanding of the universe might be incomplete. This careful phrasing from a Nobel laureate carried weight. He was not claiming cosmology was completely wrong. He was acknowledging that major pieces were missing. The crisis resembled the situation physics faced in the early 1900s. Classical mechanics successfully described most phenomena but failed completely for atomic-scale systems. Rather than abandon classical mechanics, physicists developed quantum mechanics to handle regimes where classical physics broke down. Cosmology might need a similar revolution. Lambda-cold dark matter could remain valid for describing the late universe, mature galaxies, and large-scale structure. But the early universe, the first billion years, might require new physics. Black hole formation, dark matter properties, or star formation processes might operate differently under early conditions. The Standard Model crisis was not a disaster for science. It was an opportunity. Crises drive progress by forcing physicists to question assumptions and explore new ideas. Every major advance in physics began with observations that contradicted existing theory. What made this crisis particularly exciting was that Webb was providing the data needed to resolve it. Previous generations of astronomers identified problems but lacked the observational power to investigate them thoroughly. Webb could observe the early universe in unprecedented detail, measuring the properties of universe breakers, little red dots, and overmassive black holes precisely enough to discriminate between competing theories. The resolution would likely involve pieces from multiple proposals. Perhaps warm dark matter was part of the answer. Perhaps early dark energy contributed. Perhaps star formation efficiency really was higher in metal-free environments. Perhaps black holes formed through multiple channels. Perhaps the universe was simply messier than we imagined. Whatever the solution, it would require expanding our theoretical framework. New physics was coming. The only question was what form it would take. When observations contradict established physics, one explanation is that unknown forces exist. The history of physics is a history of discovering new forces. Electromagnetism unified electricity and magnetism. The weak nuclear force explained radioactive decay. The strong nuclear force held atomic nuclei together. Each discovery revealed phenomena that gravity and electromagnetism alone could not explain. The Hubble tension hints that another force might exist. If the universe expanded faster shortly after the Big Bang than lambda-cold dark matter predicts, something had to drive that extra expansion. Dark energy provides acceleration today, but if early dark energy existed with different properties, it would constitute an additional force, active only under specific conditions. Theoretical physicists have proposed several candidates. One possibility is a scalar field called quintessence, which changes strength over time. Unlike the cosmological constant, which remains fixed, quintessence could have been stronger in the early universe and weaker now. This would accelerate early expansion while allowing later expansion to proceed at observed rates. Another candidate is axions, hypothetical particles predicted by theories that extend the standard model of particle physics. If axions existed in large numbers in the early universe, their collective gravitational effects could have influenced expansion rates. As the universe expanded and cooled, axions might have decayed or diluted, removing their influence. A third possibility involves modifications to gravity itself. Perhaps general relativity requires correction at cosmic scales. Maybe additional terms exist in Einstein's equations that only become important when applied to the entire universe. These modified gravity theories predict that expansion rates depend on cosmic epoch in ways that standard general relativity does not allow. Each proposal makes testable predictions. Quintessence should leave specific signatures in the cosmic microwave background. Axions should affect structure formation in detectable ways. Modified gravity should alter how gravitational waves propagate across cosmic distances. Future observations will test these predictions and rule out incorrect models. The overmassive black holes suggest another possible force. If black holes grew faster than Eddington limited accretion allows, perhaps magnetic fields were stronger in the early universe than models predict. Magnetic forces could confine accretion flows, allowing super Eddington feeding. This would require understanding why magnetic fields were stronger then and why they weakened as the universe aged. Some researchers propose that dark matter itself interacts through forces beyond gravity. Perhaps dark matter particles feel a dark force, analogous to electromagnetism, but acting only on dark matter. This could affect how dark matter clumps, changing predictions about structure formation and galaxy assembly. The most radical proposals suggest forces from extra dimensions. String theory, which attempts to unify quantum mechanics and gravity, predicts that the universe contains more than 3 spatial dimensions. Extra dimensions might be curled up too small to observe directly, but their gravitational effects could leak into our 3-dimensional space. If extra dimensions existed and were larger in the early universe, gravitational forces would have worked differently. This could accelerate structure formation, allowing galaxies to assemble faster. As the universe expanded, extra dimensions might have compactified further, reducing their influence and explaining why late-time galaxy formation matches standard predictions. Testing these exotic proposals requires extreme precision. The effects of new forces would be subtle, masked by the dominant influences of gravity and known forces. Webb's measurements provide some of the needed precision, but confirming new forces will require multiple independent lines of evidence. Mark Kamionkovsky, exploring theoretical possibilities, noted that one explanation for the Hubble tension would be if something was missing in our understanding of the early universe. That missing something might be a new component of matter or energy that gave the universe an unexpected kick after the Big Bang. The possibility of new forces is both exciting and unsettling. Exciting because discovering new physics would represent a historic breakthrough rivaling the discovery of dark energy or the detection of gravitational waves. Unsettling because it would mean our picture of reality remains incomplete in fundamental ways. New forces would also raise new questions. Why do these forces exist? What determines their strength? Are they connected to known forces through some deeper theory? Each answer generates more questions, pushing the boundaries of knowledge further. Physics has always progressed by discovering what we did not know we were missing. Webb might be showing us the shadows of forces that await discovery. The next generation of experiments, designed with these hints in mind, could reveal the full picture. Science is built on models. We observe phenomena, construct mathematical frameworks to describe them, and test predictions against new observations. When predictions match reality, confidence in the model grows. When they fail, the model requires revision. Webb's observations demand such revision on a scale not seen in decades. The discoveries go beyond tweaking parameters. Parameters are numbers in equations that you adjust to match observations. Changing a parameter might mean dark matter clumps 15% faster than you thought. What Webb found requires more than parameter adjustments. It requires reconsidering fundamental assumptions. Assumption 1. Galaxy formation proceeds gradually through hierarchical assembly. Small structures merge to form larger ones over billions of years. Webb found massive galaxies assembled in hundreds of millions of years, suggesting rapid formation mechanisms that hierarchical assembly cannot explain. Assumption 2. Black holes grow in lockstep with their host galaxies, maintaining specific mass ratios. Webb found overmassive black holes that violated these ratios by factors of 10 to 100, suggesting black holes and galaxies evolve independently under some conditions. Assumption 3. Star formation efficiency cannot exceed 10% because thermodynamics prevents complete gas conversion to stars. Webb found galaxies requiring near-perfect efficiency, suggesting early universe conditions allowed processes that current physics does not describe. Assumption 4. Dark energy remains constant over cosmic history. The Hubble tension suggests dark energy was different in the early universe, requiring either time-varying dark energy or additional components not in current models. Assumption 5. Cold, dark matter accounts for all dark matter in the universe. Elongated galaxy shapes suggest warm or wave dark matter might contribute significantly, requiring hybrid models with multiple dark matter types. Each assumption seemed secure before Webb. Each had supporting evidence from multiple independent observations. Revising them simultaneously requires constructing an entirely new cosmological framework that preserves what worked while fixing what failed. This reality rewrite affects more than cosmology. Astrophysics textbooks teach galaxy formation, star formation, and black hole growth based on models that Webb has challenged. These textbooks will need major revisions. Courses will need updated curricula. Decades of research built on the old framework will need re-examination. The rewrite extends to particle physics. If warm, dark matter proves correct, particle theorists will need to identify candidate. If early dark energy existed, it might connect to physics beyond the standard model. If modified gravity is necessary, general relativity needs extension. Each possibility creates work for theorists. Observational astronomy faces changes too. Previous surveys selected targets and designed instruments based on assumptions about what galaxies should look like at different epochs. Those assumptions are now suspect. Future surveys will need different strategies optimized for finding objects that should not exist according to old models. The reality rewrite is not unique in scientific history. Quantum mechanics rewrote classical physics. Relativity rewrote Newtonian gravity. Plate tectonics rewrote geology. Each revolution initially met resistance because established scientists had invested careers in the old framework. This rewrite will follow a similar pattern. Some researchers will resist, defending lambda cold dark matter and arguing that adjustments can save it. Others will embrace the opportunity to develop new theories. Younger scientists, not invested in the old framework, will drive innovation. The rewrite is necessary because reality does not care about our models. The universe operates according to its own rules, not human preferences. When observations and theory clash, observations always win eventually. Clinging to disproven theory merely delays inevitable progress. Sandro Takela, studying early galaxies, noted that this was just the beginning. With more data, researchers would be able to track how turbulent systems grew up and became the graceful spirals we see today. This optimism reflects the scientific attitude. Problems are opportunities to learn. The reality rewrite will take years, possibly decades. Webb will continue observing, refining measurements, and discovering new objects that constrain theories. Other telescopes, both ground-based and space-based, will contribute complementary data. Theorists will propose models, make predictions, and refine ideas based on feedback from observations. Eventually, a new consensus will emerge. It will not look like lambda cold dark matter. It will incorporate new physics that we are only beginning to glimpse. It will explain Webb's discoveries while preserving the model's previous successes, and it will stand as the new standard until future observations reveal its own limitations. That is how science progresses. not by defending old ideas, but by embracing better ones. The James Webb Space Telescope has been operating for only 3 years. Its mission is planned to last 10 years minimum, possibly 20 with proper maintenance. 3 years of observations have already revolutionized cosmology. What will the next 7 reveal? Webb continues scanning the sky. Every observation adds to the archive. More early galaxies, more little red dots, more overmassive black holes. Each new object refines statistical understanding of how common these phenomena are. Patterns emerge from accumulating data that individual observations cannot reveal. Upcoming observations target specific mysteries. Deep spectroscopy will measure detailed chemical compositions of early galaxies, revealing what elements existed and in what abundances. This will constrain when the first stars formed and how quickly they enriched the universe with heavy elements. High-resolution imaging will resolve internal structure in distant galaxies, showing how stars distribute within them. Are early galaxies smooth like ellipticals or clumpy like merging systems? Do they have defined centers or remain amorphous? These morphological details distinguish between formation scenarios. Time-domain astronomy will observe the same fields repeatedly over months and years, catching transient events like supernovae, tidal disruption events, and variable stars. These events provide independent measurements of distances and ages, cross-checking results from other methods. Webb will also observe objects closer to home, planets in our solar system, exoplanets around nearby stars, brown dwarfs and failed stars, protoplanetary disks where planets form, nebulae where stars are born and die. Each target provides pieces of the larger puzzle about how matter organizes itself across cosmic scales. The telescope's infrared sensitivity enables observations impossible for other instruments. It can detect water vapor in exoplanet atmospheres. It can peer through dusty star-forming regions to see embedded protostars. It can observe the coldest objects in space that emit primarily in infrared wavelengths. But the most exciting discoveries will be the unexpected ones. Every major telescope has found things nobody anticipated. Hubble discovered dark energy's acceleration. Chandra revealed supermassive black holes in most galaxies. COBE detected cosmic microwave background fluctuations that seeded structure formation. Webb has already delivered surprises: little red dots, universe breakers, black hole stars. These were not in the proposal that won telescope time. Scientists expected to find early galaxies, but nobody predicted they would break cosmological models. The best discoveries are the ones you cannot plan. Future surprises likely lurk in the data already collected. Thousands of galaxies appear in deep field images. Most have been catalogued and measured for basic properties, but detailed analysis takes time. Strange objects might hide in plain sight, waiting for someone to notice their peculiar features. Archival research will continue for decades. Students in 2050 will still be analyzing Webb data, finding patterns and objects that contemporary researchers missed. Every generation of astronomers brings new perspectives and new questions that guide them to different discoveries in the same data. Complementary telescopes will enhance Webb's science. The European Extremely Large Telescope, with its 39-meter mirror, will provide ground-based follow-up with different capabilities. The Roman Space Telescope will survey vast areas, finding rare objects that Webb can then study in detail. Gravitational wave detectors will identify black hole mergers that Webb can search for optical counterparts. This synergy between instruments accelerates discovery. Webb identifies interesting objects. Other telescopes provide additional observations from different wavelengths or higher resolution. Together, they build complete pictures that no single instrument could achieve. The next major discovery could come tomorrow or 3 years from now. It might be another population of impossible objects. It might be direct evidence for new forces. It might be something nobody has imagined yet. That uncertainty is what makes science exciting. George Rieke, reflecting on discoveries so far, noted that Webb had shown our ideas about supermassive black hole formation were pretty much completely wrong. This openness to being wrong, to revising understanding based on evidence, defines the scientific enterprise. The next discovery awaits. Webb stares into cosmic darkness, collecting ancient photons that traveled billions of years to reach its mirror. Those photons carry information about the early universe, about galaxy formation, about the nature of reality itself. When the next discovery arrives, it will reshape our understanding again. And that process will continue as long as we keep observing, keep questioning, keep pushing the boundaries of knowledge further into the unknown. After 25 chapters, after cataloguing impossible galaxies and overmassive black holes, after exposing cracks in our cosmological foundation, one question remains. What does it all mean? The discoveries are not just about distant galaxies or abstract physics. They are about understanding our place in the universe. Every atom in your body was forged in stars. The carbon in your DNA, the calcium in your bones, the iron in your blood, all originated in stellar furnaces billions of years ago. Those stars formed during cosmic dawn and cosmic noon. The universe breakers, the little red dots, the dust-shrouded monsters Webb observed are the nurseries where your atoms were created. Understanding how they formed is understanding where you came from. The overmassive black holes shaped galaxy evolution, which shaped star formation, which determined when and where planets could form, which set the stage for life. If black holes grew differently than we thought, then the history leading to Earth's existence followed a different path than we believed. The Hubble tension tells us that space itself expands in ways we do not fully understand. The vacuum between galaxies, between stars, between atoms, is not empty. It contains dark energy that pushes everything apart. The nature of empty space determines the universe's ultimate fate, whether expansion continues forever or eventually reverses. The new forces possibly hiding in the data represent physics beyond current knowledge. Discovering them would change technology decades from now. Electromagnetism's discovery led to electric power, radio, computers, and smartphones. What technologies might emerge from understanding early dark energy or dark forces? The reality rewrite forces humility. After a century of remarkable progress, after explaining everything from quantum mechanics to cosmology, physics still has enormous gaps. We do not know what 95% of the universe is made of. We cannot explain why the universe expands as it does. We cannot predict when galaxies formed. This ignorance is not shameful, it is exhilarating. Every gap in knowledge represents an opportunity for discovery. Every unsolved mystery guides researchers toward new understanding. Science thrives on problems, not on having all answers. The James Webb Space Telescope has given us problems. Wonderful, challenging, revolutionary problems that will drive cosmology forward for decades. Students entering astronomy today will spend careers working on questions raised by these discoveries. But the deeper meaning goes beyond professional science. The discoveries remind us that reality is stranger than we imagined. The universe is not a place of simple laws producing predictable outcomes. It is a place where black holes outweigh galaxies, where stars form in impossible quantities, where objects exist that theory said were forbidden. This strangeness invites wonder. When you look at the night sky, you are not seeing the static eternal backdrop that ancient astronomers imagined. You are seeing a dynamic, evolving cosmos where galaxies collide, black holes feed, and space itself stretches. You are seeing a universe still revealing its secrets. The Webb discoveries also demonstrate science's self-correcting nature. When observations contradicted theory, scientists did not defend the theory desperately. They acknowledged the problems publicly, gave them names like universe breakers, and began the hard work of revising understanding. This willingness to admit error and update beliefs separates science from dogma. What comes next depends on choices made now. Funding agencies decide which telescopes to build. Universities decide which research to support. Young people decide whether to pursue careers in astronomy. Each choice shapes how quickly we solve these mysteries. The universe is not hiding its secrets maliciously. It is simply operating according to rules we have not fully learned. Every observation brings us closer to understanding those rules. Webb has shown us where to look next, what questions to ask, what puzzles demand solving. In 1,000 years, if humanity survives and continues advancing, people will look back at this era as a turning point, the moment when our cosmological models proved inadequate and needed fundamental revision, the moment when the early universe revealed itself in unprecedented detail, the moment when we discovered that everything we thought we understood was incomplete. They will know the resolution. They will understand what dark matter is, what dark energy does, why black holes grew so fast, how galaxies assembled so quickly. They will have answers that we are only beginning to seek. But they will also face their own mysteries, their own observations that contradict their theories, their own reality rewrites. The process never ends. Each answer generates new questions. Each discovery reveals deeper layers of complexity. That is the gift Webb has given us. Not final answers, but better questions. Not certainty, but productive uncertainty. Not the end of cosmology, but its renaissance. The universe awaits. 13.8 billion years of history, hundreds of billions of galaxies, countless stellar generations, all hiding details we have not yet discovered. Webb continues observing, accumulating photons, building the archive that future scientists will mine for decades. Somewhere in that data, the next revolution waits. Another impossible object, another challenge to established physics, another reminder that reality is richer and stranger than human imagination predicts. We stand at the threshold. Behind us lies a century of cosmology that brought us this far. Ahead lies the unknown, full of promise and mystery. The James Webb Space Telescope has opened the door. We step through together into the strange and wonderful universe that is finally revealing what it truly is. The discoveries are not ending, they are accelerating. What we have learned so far is just the beginning. The greatest revelations remain ahead, waiting in the darkness between galaxies, in the first moments after creation, in the fundamental nature of space and time themselves. This is our moment. This is when cosmology breaks and rebuilds. This is when we learn what the universe really is, beyond the comfortable models we constructed from limited observations. This is when reality teaches us that it is far more magnificent than we dared imagine. The James Webb Space Telescope has shown us the truth. Our cosmology is incomplete, the universe is stranger than we thought, and the most exciting discoveries still lie ahead, waiting for us to find them.